Good afternoon, everyone. Good afternoon, class. Welcome back. And today we are going to have our tutorial session. Okay. And before we start, I'm going to take your attendance first. All right, everyone. So if you're here, just let me know through this message box. Okay. Hing Dong, are you here? Okay. Jui Min, Lu Jui Min. Right. En Hang Xiang. Okay. En Wei Hong, En Wei Hong. Ong Mei Lin, Ong Mei Lin. Feng Shui Wen. Okay, Hua Yihan, Hua Yihan, So Yan Cheng, right? Tan Xin Shen, Tan Xin Shen. Okay, Tia Liang Ho, Tia Liang Ho, Tia Yi Si, Tia Yi Si, Wong Chong Yi, Wong Ka Seng. Okay, Yong Wing Liang, Yong Wing Liang, and Yong Chie, Yong Chie. Okay, and Hua Yihan is here. Okay, Ong Mei Lin, Ong Mei Lin, are you here? Let's see. Should be here. Okay, great, excellent, full attendance. Right, thanks everyone. Okay, so we are going to discuss our tutorial today. And before that, so this is tutorial 2 from our previous tutorial session. Right, this tutorial 2 from our previous tutorial session. So we only discussed question 1 and question 2 for our tutorial. So may I know if there are any other questions in tutorial 2 that you would like to discuss? Yes, anyone, you have any of the questions in tutorial 2 that you would like to ask? Something to clarify or anything like that? None? Okay, so let's see. Now, tutorial 2, first question was on the project development tools, what you have inside the development tools. Okay, that's fine. And then question 2 was on the vector table, how you created a vector table using C. Okay, right? Then question 3. Now, question 3, I just want to talk a bit about this. Question 3, if you look at this, this is how your memory is implemented. Okay, this is how your memory is implemented. So it's divided into a few sections. Memory is divided into a few sections. I'm going to take some notes here. So I just open a notepad. Okay, now you have the most important parts of memory. There are actually 8 regions in memory. Memory is divided into 8 parts. But this is the 2 most important part, which is the part that stores your code, right? The part that stores your program code, that's your flash memory. And the part that stores your program data, that's your SRAM. Okay, so now it depends on the microcontroller. So for this particular microcontroller, 64 kilobytes of flash has been implemented, right? And 8 kilobytes of RAM has been implemented. So you can see from here that flash is always more than RAM. The reason is because of flash memory is more compact. It is higher density. You can squeeze more flash memory into the same area compared to SRAM. Okay, compared to SRAM. So your microcontroller is made from on a piece of silicon. So the real estate on the silicon is limited. Like KL, the land is limited. So when you buy a house, it's very expensive. Also, your house cannot be too big. You need to fit your budget, right? So here, that's why memory is also limited because of the limited real estate on the IC. Okay, so this is how much they can squeeze in. And normally, because your program is normally larger than data, so flash is much bigger, and also because flash is more compact than RAM. Okay, so over here, if we look at the flash program memory first, it is separated into these 4 sections. The first section is your vector table, so it is called interrupt service routine vector section. This stores your vector table. So here is all the addresses of your interrupts, or we call them interrupt vectors. Now you have to put this in. You have to fill up this section of memory with the interrupt service routine addresses. You have to fill this in. Okay, question 2 showed you how to do this in C, but normally it is done in assembly. Okay, normally it is done in assembly. So if you do it in assembly, okay, I have this, your first project, this your lab one is already open, lab one. So let me open the start file. Is this a start file? Oh, okay, this is a start file. Let's see, can I enlarge this? Oh, I can. Okay, so this is your startup file for your STM32F startup file. So what's inside the startup file? Okay, you got the uh, code for the stack, you got the code for the heap, and then this is the creation of the vector table. Okay, so how to create the vector table in assembly? You see, they use this keyword called area. Area is you define a section in memory to go into memory. Okay, and read only means that it's going to go into flash memory. It's going to go into flash memory. All right, and then reset is a special word. The area called reset, right, will always go to address 0. Oh, not this one. We always go to address 0. Okay, it always goes to address 0. Now, this is not address 0 because this section has been uh, offset. Why it has been offset? Because flash memory now is strange, but sometimes it happens. The flash memory of this microcontroller doesn't start at address 0. It starts at address 0x08. Okay, so when the vector table is placed into your memory, it will be placed at the start of the flash memory, which is actually address 0x08, not necessarily 0. So I think instead of saying start of memory, I say the start of your flash memory. Okay, start of your flash memory. So for this microcontroller, your flash memory is placed starting from this address. It's strange, but why starting from this address? You have to ask the microcontroller designer, probably because there is a bootloader program. Okay, probably because there is a bootloader program. So address 0 until 0x8000, right? Below here, there is probably a bootloader program. Right, that's the reason. If there is no bootloader program, then normally your flash will start at address 0. Okay, so this is your vector table. And this is how they build the vector table. And the first entry of your vector table is the initial stack pointer value, then the address of the reset handler, address of the non-maskable interrupt handler, address of the hard fork handler, and so on. Okay, so these are names of interrupt service routines. The names of the interrupt service routines, as you know, actually represent the address where the interrupt service routine function is placed in memory. So you're just putting the address here. DCD means you put the address here, 4 bytes each. And this is how you build your vector table. Okay, so we got our vector table. Now the next one is the text section. Text section means your code. This is your program code. So when you write your program comes here. Okay. Then the next section is the read-only data section. The read-only data section are your constants. You declare a variable called, let me enlarge this a little bit. You declare a variable called intx. Okay, fine. If you declare a variable called intx outside functions, let's say this is my int main. This is my main function. Dot, dot, dot. So you declare x outside a function. When you declare a variable outside a function, it becomes a global variable. So global variables, right, are stored in RAM. They are stored in RAM under the data section. Okay, global variables, they are stored in RAM under the data section. But what if I add const in front? Const means that the value of x, let's say I assign, let's say, okay, I call it pi. Pi is equals to 3.142, and this is not integer, it's a float. Float. Okay, so I create a variable called pi, is a float type. I give it value 3.142. And then I add this constant keyword in front here, constant. Constant means that this variable, the value should not change. It should not change. And if you try to change the value, the compiler will give you an error when you try to build. That means after you put 3.142 into pi already, somewhere else that you go and change the value of pi. For example, somewhere else you go and change the value of pi to like this. When you build this program, you're going to get an error. Compiler will tell you are trying to change a variable that has been marked as constant. Okay, so now that's one thing. The second thing is that if you use constant, this variable, instead of being stored in the data section, it will go to this section, read only data section. Because we may have a lot of constant values, right? And RAM is limited, although this is quite big, but consider relatively, RAM is limited. So where possible, we will put constant data into flash, which is much bigger instead of RAM. Okay, so those variables that are constants, they will go into this read-only data section. Anyway, the value won't change, right? So it's placed in flash. Okay, what is this data section? What is this data section? This data section is all your global variables. Okay, let's say I create a variable here, int x is equals to 35. Okay, so this is called an initialized global variable. Now, if I declare another one, I go and put here int y, right? This is called an uninitialized global variable. Uninitialized global variable. Okay, so you got initialized and uninitialized. In any case, these are global variables. Okay, so these global variables, they are placed here in flash memory. These global variables, they are placed in flash memory. Why? Why in flash? Aren't these variables supposed to be in RAM? That's because you see, RAM is volatile. When you turn off power, the entire RAM, all the contents will be gone. Right? It will be gone. All the contents in your RAM. Okay. So if these global variables they are placed in RAM, when you turn off the mouse control, then all the global variables are gone, right? Then when you turn it back on again, the global variables will appear again. How come? That's because we actually have a copy of all the global variables here in the data section in flash, non-volatile. So all these variables, they are placed here. When you turn on your microcontroller, the startup code at the beginning, the startup code will copy all your global variables from flash. You will copy all of them and put them in the data section in SRAM. Put it in this data section here. Why? Because SRAM is faster. You can read and write SRAM much faster than you can read and write flash. And also, the main issue is flash. You cannot write individual bytes. When you want to write into flash, you have to reprogram the entire block of memory. Normally, a few hundred to a few thousand bytes. Right? You have to, so it's slow. That's why it's slow. You have to write. You cannot erase and write a single byte. You have to erase and write an entire block, a few hundred to a few thousand bytes. That's why it's better we copy this to SRAM. SRAM will allow us to write individual bytes. Okay, right. So that's your data section is for global variables that are initialized, that have an initial value. So the initial value is stored here and then copied here when the program starts. How about uninitialized variables? Now, uninitialized variables, they do not have an initial value. Therefore, uninitialized variables does not take up space in the data section here. What we need to do is we just need to know how many uninitialized variables there are, how many bytes, okay, how many bytes. And then we just create this section, BSS section. This section is to store all the uninitialized global variables, right? And they are by default initialized to 0. So all your uninitialized global variables, right? When you turn on your mouse controller, they will all reside in the BSS section and all initialized to default value of 0. Okay. All right. So we know, okay, data section is for initialized variables. BSS section is for uninitialized global variables. So we are still talking about global variables though. These are global variables. Okay. So initialized and uninitialized global variables, they go to data section. Sorry. Initialized global variables go to data section. Uninitialized global variables go to BSS, right? So uh, let me just write here. Let me just write here. Okay. So this is in your data section. Okay. Uninitialized is in the BSS section, and then this one is in the read-only data section. Read-only data section. Okay. Your text is for your program lah. Your code. This is your vector table. Now, how about heap and the stack? The heap is, if you remember last time, maybe you have not used this before. But when you when you learn C++, you will have used this library before, standard library.h, stdlib.h. Okay. Now, if you have included this library, then you can use this function malloc. Malloc is called memory allocate. That means you grab some memory. Where do you grab the memory? You grab the memory from the heap. Okay, how much you want? You have to specify in bytes. So let's say I want 4 bytes. So I write like this. This means grab 4 bytes from the heap. Okay, I grab 4 bytes, but how do I use it? So to use it, you have to create a pointer. So I create a pointer, unsigned long pointer, unsigned long pointer called PTR. I create a pointer, unsigned long called PTR. Then when you do memory allocate, right, it will return you a pointer to the it will return you a pointer. Wait, let me just put this and wait that. Okay. So when you use memory allocate, you will grab a certain number of bytes from the heap. So when you grab 4 bytes, it will go up. You know, opposite to the stack. When you push things into the stack, it will go downwards. When you grab memory from the heap, it will grow upwards. Okay? The more you use, the higher it grows. Stack, the more you push in, the lower it goes. Until some point, you're going to get stack overflow or heap overflow, because memory is limited. Right. So so when you allocate, when you use the function malloc to grab memory, it's going to return you a pointer to the memory that you have just obtained, and then you can use it. So you can use that memory. How to use that memory? Then you just asterisk PTR, access the memory that you grab to do something. Use it. Okay. Why we need memory? Why we need to grab memory like this? Right? This is called dynamically allocated memory. Now you have two types of memory: statically allocated and dynamically allocated. Dynamically allocated memory is memory that you grab when the program is running during runtime. Okay, so malloc is dynamically allocated memory. You can grab memory when the program is running. This one is statically allocated memory. That means when you build the program, it's already fixed how much memory is used for your initialized and uninitialized variables. This one, the memory is fixed already. This is called statically allocated memory. So the memory, the amount of memory used is already allocated, fixed. But dynamically allocated memory can change. Right? Now, after you use the memory, you have to release it. You cannot keep grabbing memory. You run out of heap. So how you release it? Then you just call the function free, and you pass it the pointer. Okay, so this will release the memory to go back to the heap. After you grab it, you use it already, you release it back. You know why you need this? It's like rough paper. You know, when you do maths in the exam, you need to do some rough calculation, right? You only need the final answer, but you need somewhere to write out your rough calculation, your working, before you arrive at the final answer. So the same with the program. Sometimes in the program, you might need some intermediate variables, some temporary variables to store your intermediate data, right? At the end, once you finish, you get your final result already, you can remove all this intermediate data, but you need it when you're calculating. So that's where you grab memory from. That's the use of the heap. Okay, so this is a standard C library, malloc and free. These are standard C library functions. Okay, right. And the stack, what is the stack used for? The stack, right, is used for local variables. The stack is used for local variables. What are local variables? Local variables are, for example, I write here int z is equals to 5. Okay, so this is a local variable. Local variables are variables that you create inside a function. Variables that you declare and create inside a function, right? They are called local variables. And these local variables, they only exist inside the function. So when you call this function, you enter this function, z, this variable, this local variable will come into existence. How? It will be pushed into the stack. So it comes into existence, right? Now, when you exit the function, so this is the function, let's say not main, some function. You call a function, then the variable that you declare inside the function will come into existence because it's pushed into the stack, right? Now, when you exit the function, once you reach the end of the function, you exit, that variable will be pushed out of the stack, pop out of the stack, so it doesn't exist anymore. Okay? That's why you see local variables, they only come into existence when you are executing the function that contains that variable. When you execute the function that contains the variable, then the variable will come into existence. When you exit this function, this variable, it will become out of scope, don't exist anymore, out of scope. It doesn't exist anymore already. Until you call this function again, when you enter the function code, then this variable will be pushed into the stack and will come into existence again. So the stack is used for local variables. Okay, so the story about this one, I talk about this one is because to explain the code, right? So up here, this code up here, this code is actually to, this code, right, is actually to, you can read this up later, but this code, the purpose of this code is to copy, it's to copy data section from Flash, copy it into the data section in SRAM when you start up your program. It does two things. Number one is copy this one, copy here. And then number two is it will initialize the BSS section to all zeros. Okay, so in other words, like you are setting up the your data section, your initialized global variables and your uninitialized global variables. You don't have to do anything about the heap and the stack because you know heap and stack are already configured in your startup code. All right, they're already configured in your startup code. Okay, you don't have to do anything about this. All right, so that's the story of question 3. I just want to tell you about these terms, okay, because you might encounter them. What is the difference between static local variable in a function and global variable outside the function? Looks like they are the same. Yes, they are the same. Now, if I have a local variable, that is a very nice question. If I have a local variable, right, called this z, what happens if I put static in front? Okay, if I put this static keyword in front, if I put static keyword in front, what the compiler does is the compiler will put this variable inside data section. Okay, when you add the static keyword in front of a local variable, the compiler will put this local variable into data section, not in the stack anymore. So that's why static local variables, right, they continue to exist even after you exit the function because they are not placed in the stack, they are placed in the data section. Okay. One more thing on the add. You see, the opposite of static is auto. Auto, right? This is default one. So normally, you just write like this. You just write int z equals to 5, right? But actually, there is auto in front. This is the default. So local variables are by default automatically created variables go into the stack. Okay, so if you don't want them to exist temporarily, you want them to exist permanently, then you just put a static keyword there. So then you might ask, then what's the difference between this variable and the global variable? The difference is visibility, scope visibility. Although this variable will exist throughout program execution, but this variable is only visible inside this function. Outside this function, nobody can see Z, nobody can use Z. Z can only be used and seen inside this function. So it has local scope, while this guy has global scope. Everyone can use this variable, can see this variable and use this variable. Okay, all right, good question. Okay, all right, next now. Okay, so we have seen question 1, 2, 3. Now question 4 is volatile. This one I talked about it in our lecture videos already. Okay, and then question 5 on the pointers, I also talked about it in the lecture videos already. Question 6 theory question: what's the purpose of CMSIS? Cortex microcontroller software interface standard for standardization, right? For standardization. You see here, you got all your CM. Okay, let me show you. Let me show you. Let me show you. Okay, you see, this is your header file. This is your STM32F header file. You know, if you use LPC1768, you got the LPC17xx.h header file, right? If you use STM32F, you got the STM32F10x.h header file. So you must have this header file because you get all the names of the peripherals from this header file, right? You want to access peripherals, GPIO port, the registers, the names are all inside this file. Okay? Unless you go and declare the pointers yourself. Otherwise, you just use it from this file because everything has already been declared for you. Now, you see what's so special about this file is your main program only need to include this file. You see, your main program, your main programmer is the file that contains the main function, right? The file that contains the main function, in this case, blinky.c, it has your main function. So this is your main file. So you see here, it includes this header file. It includes this header file. So when you include this header file, this is the mother of all header files. You must include this. Why? Because after you include this guy, you see, this guy, right? He will then include all the other files that you need. So let's see. First of all, he's going to include blah, 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 blah. Where is it? There it is. So next is going to include your core CM 3.h, this header file, which is this guy. Now I open the core CM 3.h. Okay, this is your core CM 3.h. Okay, so what's inside core CM 3.h? Core CM 3.h contains all the functions to access your processor core. The functions to access your processor core. What is one example of the processor core function that you already know? Systick config. This week you learn about the Systick config function, right? So you use the Systick config function to configure the Systick timer inside your processor core. So the processor is standardized one. No matter what microcontroller you use, as long as it's a Cortex M microcontroller, right? They all use the same processor. That's why this is a standard file. Okay, so what is an example of the function? Okay, let's look for, I don't want to scroll through this file very long. So let's just look for Systick config. Is it here? There it is. Get Systick config. Blah, blah, blah. Okay, so this is the function. Let me minimize it a little bit. Okay. So this is the Systick config function. It's defined inside this header file. Okay, so it will receive the number of clock ticks and then return you a 32-bit value. Okay, this is the code like you see. So it will set up your reload value and your control register values. It will clear your current value. Then you also set your enable your interrupt priority, okay, and stuff. So it's all here. Now, I just want to show you this only. So I go back to this one. Right. So now you know this file. This file contains all the functions. There are many other functions to access the peripherals inside your processor core. Then this one is the file to initialize your system clock. Initialize your system clock is inside this file. And then this one, standard integer.h, stdint.h. This is a standard C library file. What's inside this file? Stdint.h. Okay, let's go to stdint.h. I show you the important part of what's inside this file. Okay, you see these guys? All right, so this file, he type define sign char. Instead of calling it sign char, you can now call it by an alternate name, which is actually more meaningful, int8 underscore t. So this is an integer 8 bits type. Okay, then you have integer 16 bits type. And then you have, for example, unsigned integer type unsigned integer 32 bits. It's much more informative than reading this, right? When you read this program, unsigned integer, then you might ask, how many bits? But if you write it using this uint32 underscore t, then it's very clear when anybody read the program, they know, oh, this is an unsigned integer 32 bits. So this is a better way of writing things. It's a much better way. It is in stdint.h. So inside this file. So this is just to show you actually when you build your program, right? In order for this blinky.c to build correctly, actually it needs a lot of header files. And all these header files are called in by the code. Okay, so they are all related. They are all in. We call this the dependency. These are the dependencies. These are all the files that you need for blinky.c to build correctly. Okay, all right. So I come back here. So that's CMC's file, CMC's standardization, right? Okay, these are all these theory questions, all theory questions. Okay, so all theory questions. For example, this one. For example, this one. Identify and describe any three CMC's core functions to access special instructions. Why do we need this? It's because we know that we can write our program in C, and then when you build, the compiler will translate all your C coding into assembly instructions. That's all fine and nice, but there are certain assembly instructions, right, that cannot be generated by your C compiler. Okay, you just cannot get the C compiler to create certain assembly instructions. What are they? For example, is the do nothing, NOP, or the wait for interrupt. This is actually go to sleep. This instruction put the processor to sleep. Why we put the processor to sleep? Don't waste power. Let's say we want to wait for an interrupt to happen. While waiting for the interrupt, I don't want to keep looping. That's a waste of battery power, like it's battery operated. So we just power down the processor. The whole microcontroller go to sleep. And then when there's an interrupt, it will wake up and resume operation. So how to put the processor to sleep? Well, the assembly instruction is WFI. But if I'm writing in C, how do I do it in C? If you want to do it in C, then you just write this underscore underscore WFI. See this? So you can do it either in uppercase or lowercase, like it's the same thing. W underscore underscore WFI is a function. So you have to open close bracket like this. It's a function. So if you want NOP, it's also NOP will be underscore underscore NOP like that. So this allow you to execute special assembly instructions in your C program by just writing like this. So when you write like this will power down the CPU. Okay, this one is do nothing for one cycle. Right? You can't do these things in C1. You have to use assembly, but you're writing in C. So how to use assembly in C? We can use these guys. So these guys, they are called intrinsics, right? Intrinsics. Intrinsics, they are special functions there are special functions provided by the compiler, right? Let me full size, which substitutes the intrinsic with the assembly instruction of the targeted processor, right? So to perform that operation, which has no equivalent in C, right? So these are just theory. So if you go to this file, where's the file? cmsys armcc.h, cmsys armcc.h. Okay, so that file is here. cmsys armcc.h. Where are you? Where are you? Let's see. Core. Oh, I think it's one of these. It's not that one. Maybe did I write it wrongly? Where did I write? I think it's probably from, yeah, this microvision 5 because I'm using microvision 4. So microvision 5 version 5 uses this armcc.h. Version 4 slightly different. Version 4 uses this one, cmsys core m instruction or function. So let's look at this instruction. Let's look at this one. So it's defined here. You can see here. It's defined your NOP, your WFI, WFE, SEV, ISB. So it's all fine here. So let's read the description. CMC's Cortex M Core instruction access header file. Okay, it's automatically added. So then you can access all these. You can access all these functions, all these instructions as a C function. Okay. All right. So do you have any questions? If none, I'm going to give you something to do. I'm going to give you something to do. I'm going to give you this one to do, right? Now, last year, when we first started study from home, nowadays everyone is working from home. So last year we started study from home. So we had to make sure that students follow what is happening and they don't drop out of the class, because we don't know. So one way is to have a test every week. So your seniors, right? Last year, your seniors, every week they have a weekly test, which carries coursework marks weightage every week. So they were very stressed, and they told me that they feel really stressed. So I removed that this semester. But you know what? I had 100% passing rate last year. Right? Everyone passed. The reason is nobody studied before the exam. Everyone studied throughout the semester because there is a test every week. So they were on their toes. Everyone was on their toes. They have to keep studying to keep up to date because the moment you don't study or you don't follow what's happening, or then you won't be able to answer the test questions already. So this is very good, right? So I hope that everyone you will follow, keep up with the classes. Okay, now it's only week 5. So make sure that you don't fall behind. Make sure that you have watched all the lecture videos until week 5. You have read all the lecture discussion, all the lecture notes, and you have done all your tutorials and you have done all your labs. Right? That's the only thing you need to do to guarantee pass this subject. Right? Just make sure that you follow everything that's happening, and I guarantee that you'll never fail this subject. You just need to make sure that you follow the class. Okay? Don't leave the material. Is it okay? Maybe I read next week, because next week we're going to study something else that is going to build on what you learned this week. So if you don't follow and understand what's happening this week, next week you will be lost, and the week after that you'll be even more lost. So then you will start to lose motivation, and then you feel depressed. Okay, so don't go into that state. Make sure that everyone stay up to date with the materials. Okay. So I'm going to give you this tryout now, right? Since if you have finished tutorial 2, you have absolutely no problem answering this question. So take 10 minutes to answer this question. We will discuss it at 4:50. Okay, you can start now. Okay, class, right? So let's look at this question now. All right, let's look at this question. Okay, so now this question, we have a microcontroller peripheral, right? We have a microcontroller peripheral with three registers: control, config, and calib, located sequentially in memory starting from address 400, right? Okay, how does this look like? So if I draw this out, then this is your memory, and this is your address. Okay, so it will look like this. So this is address 0x40000000. Okay, this now it's because it's 32 bits, 32 bits, right? Each of these is 1 byte. Memory is normally uh, arranged like this, right? In bytes. Memory is normally arranged in bytes. So if you have a 32-bit register, 32 bits will be 4 bytes. Okay, so this is your control register, and then you have another 4 bytes starting from 0x40000004 for your second register, which is config, and your third register, which is calib, will be from 4, 5, 6, 7. This would be 8. 8. Okay, so how do we access these three guys? Well, an easy way to access these three guys is using pointers. So what we do is I have a pointer. I call it I now this is 32-bit value also unsigned integer 32-bit unsigned integer 32 bits. This is a 32-bit value, and I want to create a pointer. So like that pointer. Okay, then I cover this in a bracket, right, and give it a value of 0x40000000. So I am creating a pointer to a 32-bit value, and I give this pointer this address. That's fine. Okay, so I have this a pointer to this location already. Then I access whatever the pointer is pointing to like this. So I use this to access whatever the pointer is pointing to. Okay, that's great. So now I can access control already. So if I want to clear control, then I just do like this, equals to 0x00000000. So then I can clear the contents of control. But this is not nice, right? So why don't we give it a nicer name? So we give it a nicer name using hash define. I define an alternate name for this. I call it CTRL, right? I call it CTRL. So in your program, if you want to clear the contents of CTRL, you don't have to write like this. A better way is you can just write like this, right? Both of these are the same. Both of this one control equals 0 and this one they are the same because I define control to be equals to this, right? So similarly, I got another two, right? So I create another two more pointers. I create another pointer called config, which points to address 4, and I create another pointer called calib, which points to address 8. Nice. Okay. Now one more thing that I forgot to put. These registers, right, are peripheral registers. So peripheral registers, we should always add the keyword volatile to avoid, because the value of peripheral registers can change outside processor control. The value in peripheral registers, right, that can change. Although the processor, you never write any code to change the values, they can change by themselves. Why? Because, for example, you have the GPIO port connected to a push button. When you press the button, the value in the GPIO port will change, right? Okay, and this is controlled externally by the push button. You never write any program to do this. So these sort of variables, we have to add the keyword volatile. Okay, so this is the answer for part A. Write preprocessor directives to allow access to these registers using pointer method. Okay, but now this is fine, but you see, what if I got 4 instances of this peripheral? Let's say this peripheral, this is just one instance. What if I got four instances of this peripheral? Four instances means now 4 instances means that this is control 1, config 1, calib 1. Then you got another 3. You got control 2, config 2, calib 2. And then you got control 3, config 3, calib 3, control 4, calib 4, config 4, and so on. Just like you got your GPIOA, GPIOB, GPIOC, GPIOD. I got 4 instances. Am I going to create a pointer to each of them? Oh, that is troublesome, right? So a better way is we don't create a pointer to each of them. What we do is we create a data structure. So I define a new data type, which is a structure. Okay, and inside this structure, I have 3 members. I have 3 members. I have 1, 2, and 3 members. I got 3 members. The first one is CTRL. The second one is config, and the third one is calib. So I got 3 members inside this structure, and I call this structure MCU peripheral type type def. MCU peripheral type def. I call this. Okay. So then I define. Then I define peripheral one. All right. I define peripheral one. I define peripheral one as a pointer not to 32-bit value anymore. I declare peripheral one. All right. It's actually a pointer to this data structure. So I got this data structure, right? It's a pointer to this data structure. So this data structure, I'm going to put this address. Okay, so now I can access the members inside. Okay, let me finish this first. Let me finish this first. So I got 4 peripherals, right? I got 4 peripherals. The first instance, the second instance, the third instance, and the fourth instance. So where do they start? Okay, the second one starts at, yeah. Okay, the second one starts at C, and then the third one starts at 1, 8, and the fourth one starts at 2, 4. 2, 4. Okay, so like that, right? So now I only need to create 4 pointers to each of these data structure. Now, if I want to access peripheral 4 control register, how do I do it? If I want to access peripheral 4's control register and put 0 there, I just do like this. Okay, because peripheral 4 is a pointer. This is a pointer. So when you use a pointer, when you want to access the member of a structure, right, and you're using a pointer, you have to use this arrow operator. Okay, so the structure peripheral 4, I want to point to this member inside, and then I give it this value. Okay, so this is how you do it. And it's much more efficient compared to this one. If you use this method, I got 4 peripherals. Each one got 3 registers. Then I have to have 12 defined lines, 12 times the define. But this is neater and much more memory efficient. Okay. All right. Do you have any questions for this? Everyone okay with this? Now this is very important because if you look at your header file, you go and look at your header file, you will see that okay, for example, this is okay, where is my, I want to show you the GPIO. I want to show you the GPIO. Where is my GPIO? GPIO. You know, you got your CR, registers. There it is. Okay. This is your STM32F microcontroller. So this is GPIO type def. GPIO type def. And then you got the CRL, CRH. Now this is volatile. Underscore underscore IO is actually volatile. Where is it defined? Is here. Where is it? Yeah. Underscore underscore IO. Where is it? Oh, it's not in this file. It's in one of those files. You just control F, you can find it. It's not in this file. It's in another file. So underscore IO is actually volatile. So you got your CRL, CRH, input data register, output data register, and so on. I'm sure you know about this already. You start doing your assignment. Okay. So how about the this one? How about this one? Assigning addresses to the pointer. So where is this? So here you just GPIO type def. I copy this and then I look for GPIO type def. Where is it? Okay. So hash define GPIOA is it's a pointer to, oh sorry, this one I shouldn't have this. Shouldn't have this. Because this is a pointer, I don't need to access whatever is pointing to. Okay. So here, GPIOA, it's a pointer to GPIO type def, and you give it address GPIO base. What's GPIOA base? Then you just search for GPIOA base. So you see, GPIOA base is APB2 peripheral base plus this one. Okay, what does this actually mean? They actually write it this way. I can show you. It's actually you write it like this. Instead of writing like this, I can write here. I can write a hash define base address. Hash define base address is this one. This is my base address. Then instead of writing this, I just write base address plus 0. And then this is base address. This is the way they write in your header file. Standard way of writing your header file. Like that. Why they write it like this? So if your base address changes, I don't have to change this one and this one and this one. I don't have to change all this. I only need to change this. Okay, because everything follow this base address. So this is a more neater way, a more organized way of writing your code. Okay, and this is how they write your header files. Okay. So the last part of this question, part C, identify variables that should always be declared with the volatile keyword. Provide an example. The answer is this one. This is the answer. It's inside your tutorial. If you did a tutorial there, you know that the answer is the answer is question 4. Question 4. Yes. This is the answer for which variable should always be declared volatile keyword. Provide an example. Oh, same question. Same question. Okay. All right. So, do you have any questions? Okay, if no questions, then everyone, you can make sure that you follow the classes. If you are slightly left behind, then try to catch up. Okay, and if you have any problems at any parts you don't understand, just let me know and I'll give you a better explanation. Okay, so try to catch up with all the materials until week 5. Okay, and with that, we end our class here. Can find the test question at Classroom. Oh, I didn't upload this test question to Classroom. This is just a tutorial exercise. You can take a print screen now if you want. Okay, so everyone, you can take a print screen now. Right, just take a few seconds, print screen this, and then I give you the answer. I give you the answer to print screen as well. Okay, everyone, print screen already? All done? Okay, so now I'm going to give you the answer. Print screen already? 5, 4, 3, 2, 1. Okay, this is the answer. Let's go to Steve. Okay, so you can print screen this. This is the answer. Actually, there are different ways of writing the answer. It's not just one fixed way. This is just one sample answer. This is a sample answer. Okay, so the next tutorial class, again, I'm going to give you some exam type question to try out again on top of discussing the tutorials. So try to keep up to date so that you can know how much you will get. This is very good practice to gauge how much you will get for your final exam. So every week, if you do these tutorial test questions and you get full marks, you know your final exam, you're going to get A lah. And every week, if you do these questions, you find that you cannot get 50%, no, then you're going to struggle for the final exam. And then you need to know, you need to study more. Okay, so it's a good preparation, and we start doing it now. Okay, good work, everyone. Thanks for staying up until 5:06. Have a nice weekend. Thanks, everyone.